in between metals. Metals which are found in between group 2 and group 3 of the periodic table. Therefore, we call it as transition metal. Another name you'll learn in the A level next year is they are also known as D block metals. They are also known as D block. D block, B-L-O-C-K metals. So we also call them as D block metals. So you'll learn about it in grade 11 next year, or this year in August, when you start learning about the transition metals. So I hope you understood what is the meaning of transition metals. So transition metals are those metals which are found between group 2 and group 3 of the periodic table. Now let's go deeper into the transition metals. Okay, let's change it. So transition metals and alkali metals. So how do the transition metals compare with the alkali metal? So here we are comparing the alkali metals that is found in group 1. We have sodium in the alkali metals. Remember, group 1 we have metals like lithium, sodium, potassium, rubidium, cesium, francium. So they are all in group 1. We call them as alkali metals because they form alkali. So when we compare the alkali metals with the transition metals, that's what we are now going to talk about. So how do the properties of transition metal compare with those of alkali metals? Compared to alkali metals, the transition metals are harder and stronger. That means much more harder and stronger. But they cannot be cut with a knife. Remember, the alkali metals could be cut with a knife, but we cannot cut the transition metals with a knife. They are more dense. This means in a fixed volume of metal, there are more atoms of transition metal than they are of an alkali metal. So most of the transition metals are very dense. So what does that mean? They are also heavy. Next, they have very high melting and boiling point except mercury. Remember, we are going to get some questions, so please pay attention. Then only you will be able to answer those questions. So pay attention. So they have very high melting edge, less than alkali metals. Much less reactive than alkali metals. So when we talk about the chemical properties, the transition metals are much less. If you see the transition metals like lithium, sodium, they are very reactive, but transition metals are not reactive. Then they tend to react relatively slowly. For example, with air, water and acid, they'll react very slowly. They react but very slowly. Copper does not react with water, whereas alkali metals such as sodium reacts vigorously. So you can see the difference. Copper, if you put in water, it won't react so easily. But alkali metal, as soon as we put it, sodium, as soon as we put in water, it will react, giving out heat. So very reactive alkali metal, but transition metals are much less reactive. Copper does not burn in air, whereas alkali metal such as sodium burns vigorously. So this is again some properties the transition metals are. So just first two lines, please write it down. the first two lines. And how reactive are the transition metals? We just now saw that transition metals are much less reactive than alkali metal, and they react very slowly. The general trend is for a decrease in reactivity from left to right across the periodic table. So if you go to the periodic table, you'll see that their reactivity decreases. There are exceptions such as zinc, which is more reactive than expected. Zinc is an exception, but otherwise that normal trend is what? As we move left to right, we see that the reactivity gradually decreases. That means scandium is more reactive than titanium. Titanium is more reactive than vanadium. Vanadium is more reactive than, no, decreases. Scandium is, general trend is for decrease in reactivity. Yeah, that's what we are saying. But zinc is a little different. It's an exception. It is more reactive. So remember that. So if I ask you which is more reactive, manganese or iron, what will be your answer? Manganese is more reactive because it decreases in reactivity as we move from left to right. Another exception is iron, which does not quite really react quite readily with air and water, causing rust, which does react quite readily. So we all know what rust is and how iron forms rust. Remember, iron is also a transition metal. We were recently studying about corrosion and rusting. So another exception is iron, which does react quite readily with air and water, causing rust. So the question over here is, what is, yeah. So rusting is an oxidation reaction between iron, oxygen and water, which leads to the formation of hydrated iron 3 oxide. Yeah, good. Fe2O3 XH2O. Yeah, because water varies. The percentage of water varies in rust. So rusting is an oxidation reaction between iron, oxygen and water, which leads to the formation of hydrated iron 3 oxide, the chemical name for rust. So remember this, hydrated iron 3 oxide. Rusting is a type of corrosion. Rusting is a type of corrosion. Corrosion takes place in all metals. What are the word and chemical equation for formation of rust? So this is the word and chemical equation for rusting. Can you write it down, please? And then, sorry. When transition metals do not react, they lose electrons and form positive ions. So we all know metals will lose electrons and form positive ions. Some transition metals only make one type of ion. For example, like silver will make only one type of ion, Ag+. Zinc will make Zn2+. But most transition metal can form more than one type of ion, as they can lose different number of electrons. For example, iron has two valencies. One is iron Fe2+ and the other one is Fe3+. So we can see that transition metal shows variable valencies. So that's one of the most, one we know they show colored compounds, and we'll come to that. Then they show variable valency oxidation state. So we can write down on the top or at the bottom. What does it show? It shows, I'll just write down there, variable, VARIABLE. I think so, the spelling is correct. VARIABLE, variable valency. VALENCY, oxidation state. OXIDATION, oxidation state. STAT. So transition metals show variable oxidation states. Better to write the S over there. So variable oxidation states. For example, iron will form Fe2+ and Fe3+ ions. So they show variable valency, excepting silver and zinc. Silver is Ag plus and zinc is Zn2 plus. Otherwise, others will show more than one type of ion, and we call that as variable valency oxidation state. Please, can you write that down? Number 1, transition metal will show variable metals, metal compound, transition metal compound. As most transition metals can form different ions. This means they can form multiple compounds. For example, copper can form copper 2 plus, which can make the red compound, copper 2 oxide. See how when it has a valency of plus, and when it has a valency of C2 plus, which can make black compounds. You can see how it becomes different. Both are copper, but one is copper plus and one is copper 2 plus. And copper plus is Cu2O, it will be a red compound, whereas copper oxide, which is C2O 2 plus, will be CuO. So see the difference between them. First one we call as copper 1 oxide, and the second one we'll call as copper 2 oxide. So this is how the difference can be seen, because they have different variable valency. The number in the bracket indicates how many electrons have been lost. So when we say copper 1 oxide, it has lost 1 electron. When we say copper 2 oxide, it has lost 2 electrons. So see the difference of the transition metals and their difference in having a variable oxidation states. When these elements form compounds, they have different property and different color. So this is one very good example. Now, most transition metals form colored compounds. Most of them, they'll have colored compounds. For example, iron 2 oxide, FeO2 is black. Then we have iron 3 oxide. If you look at iron, that is FeO, okay, that's when we talked about iron, this Fe2 plus Fe3. So remember that, okay, this is 2 is not there, so FeO. Put that there. Yeah, so FeO is black in color. Then iron 3 oxide, Fe2O3, is red brown when hydrated. This is rust. So iron 3 oxide is red brown and iron oxide is black. Remember these examples. Then copper 2 sulfate with water is blue. This can be turned white by heating the crystals to the water. So copper 2 sulfate crystals are blue in color. So see the color differences. So the color of many gemstones come from the presence of transition metal compounds. For example, gemstone jade contains iron. The colored compound of transition metal can also be used in many ways. Some ways are to color stained glass windows, to color paints, as colored glaze on pottery. presence of transition metal ions in a solution can be tested by adding sodium hydroxide solution. So again, this is chemical property. So the presence of transition metals ions we can identify by using NaOH solution. So therefore we'll know what transition metal is there, because it will form a precipitate hydroxide. Once more I repeat, the presence of transition metal ions in a solution can be tested when we can add sodium hydroxide with it. It will give a particular precipitate of that color. So by that we'll know what precipitate or metal hydroxide, transition metal hydroxide is present because of their unique color. For example, if transition metal ions are present, a metal hydroxide is formed. This is insoluble and so appears as a solid called a precipitate. Different metal ions produce different color precipitate. Like iron 2 ions produce a grey-green precipitate, FeOH2. Iron 3 ions, ferrous 3 ions produces an orange-brown precipitate of FeOH3. So here what we are learning is when the transition metal solutions, ions in a solution, it can be tested by adding NaOH solution. Why? Because it will form insoluble precipitate of particular colors according to the transition the metal. Iron 2, ferrous 2 or iron 2 ions produces a grey-green color of iron hydroxide, whereas iron 3 ions produces an orange-brown precipitate. See how the difference comes according to the variable oxidation state, and we can recognize this is iron 2 and this is iron 3 by the color differences. Suppose somebody tells you, please recognize whether this is iron 2 or iron 3. It is iron only, but it's iron 2 or iron 3. We will put it in solution of sodium hydroxide and it will form a precipitate grey-green. Then it is iron 2. If it forms a precipitate orange-brown, then it is Fe3+. So I hope you understand how we test the transition metal by adding metal hydroxide. Once we add metal hydroxide solution, it will give a specific colors of precipitate. Copper ions will produce blue precipitate. Position. Now this topic is when we heat something, it will broken down. So compounds of transition metals can be broken down into simpler substances by heating them. Next property, chemical property, is when we heat transition metal compounds, it will be broken into simpler substances. This is called thermal decomposition. For example, metal carbonate, suppose it is magnesium carbonate, copper carbonate, they will be broken down into metal oxide like copper. If it is copper carbonate, it will break down to copper oxide plus carbon dioxide when heated. So this is known as thermal decomposition. Thermal means heat and decomposition means when we break it down. So when we heat a substance, it will break down into simpler metal oxide and the different gas like carbon dioxide. If it's a carbonate, then carbon dioxide gas. The reactants and products are different colors. So the reactants will have one specific color and the products will have one specific. How can the presence of carbon dioxide be tested? Anybody in the class? Can you tell me how we can? So the gas produced can be bubbled through lime water. If the gas is carbon dioxide, it will turn the lime water cloudy. So that is a test for carbon dioxide. Good, Leo. Only the formula you have to write the correct formula. Alright, thermal decomposition of iron carbonate. So iron carbonate, FeCO3, if heated, It will give you iron oxide and carbon dioxide. What is the reaction when copper carbonate undergoes thermal decomposition? Anybody in the class? It will break down into CuO plus CO2. So that's thermal decomposition of copper to carbonate. I hope this is